And when I received this beautiful book at the entrance of the corridor, I opened it randomly, and the following quote confronted me. In the long run, the byproducts of nuclear science, means quantum mechanics, may be more important to the physical sciences than the direct result of initiating new sources of energy. So practically, these byproducts, for example, will be my talk this morning about quantum computing and communications, which is really founded and rooted in the works of John von Neumann. Okay. So, probably you remember that this last weekend was very hot in Hungary, around 31, 32 centigrades. And Saturday afternoon, as I was sitting under the big walnut tree in our garden. This tree was planted by the grandma of my wife. And when I was thinking about my today talk, a Hungarian folk song came into my mind from Transylvania. For the English-speaking audience, I translated. This is a raw translation, and it sounds like this. Sorry, I won't sing it. I only read aloud because my voice is not so skilled. So, this walnut tree was planted here by my grandfather. He did not sit in its shade. He did not eat its fruit. He didn't do it for his own benefit, but for someone else. Therefore, his grandchildren bless his memory. So, of course, we can be regarded as engineers dealing with quantum computing and communications as the byproducts of John von Neumann, but I would rather say that we are the fruits of his walnut tree, because quantum mechanics, which is the basics of this quantum computing and communication topic, is founded and mathematically formalized by John von Neumann. Okay. The main topics of my today's talk will cover the basic rules of quantum mechanics, the nanoworld. I apologize, mathematicians and physicists in this room, because I will approach from the engineering perspective. So please forgive me if I'm not as precise as you mathematicians or physicists. So I will give you an interpretation of the postulates, and I will highlight some consequences. And because we are engineers, we would like to apply what the mathematicians and physicists already discovered. Therefore, I will give you an insight into the world of quantum computers and quantum communication devices, and of course, the applications. As in the introduction, it was highlighted that I am the research director of the Quantum Information National Laboratory of Hungary. This organization organizes the efforts, the quantum technology efforts here in Hungary, and I would like to illustrate the results in the field of quantum computing and communication by the results of the Hungarian teams as well. Okay, so when we are speaking about quantum mechanics, I brought here two quotes, one from Einstein. You are probably familiar with this quote: God does not play dice with the universe. And there was another interesting, at least for me, interesting quote from Max von Laue, who is also, or who was also a Nobel laureate. He said, when he heard about the final solution for the quantum mechanics, that if that turns out to be true, I will quit physics. And this is the reason why quantum computing and communication had a bit delayed compared to nuclear technology, because this strangeness of quantum mechanics was, I'm convinced that the good approach to handle quantum mechanics is in accordance with the motto of NASA. So the aerodynamically, a bumblebee body is not made to fly. The good thing is that the bee doesn't know it. So we need to apply the quantum mechanics and we should be or must be convinced that it is a valid description of nature. And as engineers, we need to find how can we utilize quantum mechanics. Here is only a picture about the market actually related to the quantum computing and communications. This is a $30 billion market in 2022, and it has a 20% increase compared to the previous years. And I would like to call your attention that this is a foreign chart, but there is Hungary in the middle in the blue box. So we were mentioned, Hungary, as a player in this world. Okay, but if we would like to go closer to quantum mechanics, it is worth investigating the dimensions of the universe, the distances between the biggest dimensions and the smallest one, and it is interesting where the human being is standing between the largest and the smallest. Okay, I will use, or you can use your nail of your thumb to measure the universe. So my question is that if you put your thumb towards the sky on a starry night, how many stars are covered by your fingernail? Any estimation or guesses? Million? 100 million? Billion? Oh, it's good. Okay, I give the solution. Okay. So you cover 15,000 galaxies, and each galaxy has in average 1 billion stars. So the number of stars, and so somehow the size of the universe can be represented by this huge number. On the other hand, if we go down to the level of the elementary particles, which behave according to the quantum mechanics, this is around or below the nanometer range, then you can use your nail to represent this dimension, because your nails grow 1 nanometer, of course, in average, during 1 second. And where is the human being standing, or are standing? Oh, there is a number at the top of the slide. So the number of stars we already discussed. So this huge number meant or referred only to the stars under your nail of your thumb. But the whole number of stars in the universe is the same number as the grains of sand in the Sahara Desert. Or if you compare the number of atoms within you, is more or less a bit larger than the stars in the universe. So Blaise Pascal formulated a very good answer to the question, where are we standing in the universe? For after all, what is nature? And nothing in relation to infinity, all in relation to nothing, a central point between nothing and all, and infinitely far from the understanding either. But we know, thanks to John von Neumann, that we are closer and closer to understanding the nature around us. As I mentioned, I am an electrical engineer, so I am dealing with technology and not pure mathematics or physics. So this is a typical life cycle of an invention. This invention is the steam engine. Roughly 2,000 years ago, Herons constructed his ball, which is based on the steam engine principle somehow. And after 2,000 years, we prepared and developed efficient and more efficient steam engines. On the bottom left picture, there is a steam cylinder of the Titanic. This is a huge monstrum with great efficiency among the steam engines. But when we decided to fly with engines, then we realized that the steam engine, the efficiency of the steam engine is not enough to rise the plane to the air. Therefore, we need to stop, think, and find something new principles which make possible to the engine-based flight. This is the explosive engine. This is the case in computer science or computers. So most of you, I'm sure you are familiar with the Moore's law, which states that the number of transistors, the basic building blocks on a microchip, doubles about every 2 years. Similarly, the cost of the computer is halved. But the principle behind this observation is that we design and implement smaller and smaller transistors. Therefore, we can use more and more transistors. Therefore, we can be faster and faster. But there is another consequence of the Moore's law, namely, if we count the electrons per device, the electrons per transistors, when we design smaller and smaller transistors, we will reach the region when only one electron will be contained by the transistor. And in this case, one thing is sure, that the transistor works differently as we expected. And this is the range about I am speaking. This is the nanometer or smaller scale, where the quantum mechanics, described by many scientists, but among them John von Neumann also played an important role. So this quantum mechanics describes the rules of how the nature behaves at this scale. Practically, there is only 4 postulates. It depends on, we engineers are saying 4 postulates, physicists sometimes mention 5, but the important thing is that there are several very simple rules for the quantum mechanics. The question is, why do we learn Newtonian physics in the primary school instead of quantum mechanics? The reason is because these rules are quite strange and seem to contradict to the human logic sometimes. So we will go through these basic rules, these postulates from engineering point of view. You are familiar with the phenomenon of classical bit. This is an information containing unit. It can have 2 logical values, either 0 or 1. I brought here a demonstration device, a 100-forint coin. So it has a head and tail, and it can be regarded as a logical 0 or 1. And on the right-hand side of the slide, you can see a picture of Claude Shannon, who formulated the basics of information theory and defined the so-called Shannon entropy. This is related somehow to the information content of a classical register or a classical bit. Compared to the classical bit, a quantum bit can be regarded as a flipping coin in the air, which contains or carries both values at the same time. So you can realize the difference between the mathematicians and engineers, because Professor Neumann and Professor Sass were able to imagine a coin and the 2 sides, head and tail, without a real coin, but electrical engineers, we always need something to hold in your hands, and we are convinced only if really flips in the air. So practically, the first postulate of quantum mechanics formulates or says that a quantum bit can carry 2 different classical values at the same time. And if we take the second postulate, we can turn to the chess. Both professors mentioned chess as an important part of the game theory, but it is important from quantum computing as well, because probably you are familiar with the story of the invention of chess. So when the wise man went to the Shah that he's invented the Shah was really satisfied and asked him what price he would like to get for the chess. And he said that please put 1 piece of grain one piece of grain on the first field of the chess table, twice as much, two pieces of grain on the second, and he would like to only get the grains on the last field of the chess table. I counted here the top blue number is the number of grains on the last field of the chess table, and this is roughly 70 billion tons of grains, which is the price of this invention. And the EU production is only 210 million yen. So what I would like to emphasize that this exponential calculation or behavior which appears even in the quantum mechanics is very important from computing point of view, because we can store two values in one quantum bit, we can store 4 in 2 quantum bits, and if we consider only 500 quantum bits, 500 electrons or 500 photons, it will contain more numbers than the number of atoms in the whole universe. So it suggests that somehow we will be able to store information in a very comprised manner, but not as comprised as you think, because there are some randomness in the quantum mechanics. But anyway, this is a good start to build quantum computers. There is another consequences of merging quantum bits into quantum registers. Enrico Fermi said that it is worth making experiments because there are two possible outcomes. Either the result of the measurement confirms the theory or the hypothesis, then we are satisfied that we have a good theory. Or, contrary, if the result is contrary to the hypothesis, then we made a discovery and we can follow the new tracks. So let me make a total experiment. Let me consider two coins. First, we consider them classically. If we have two coins and we flip both coins into the air and let them fall, then we will have four different final state of the system, either 0, 0, 0, 1, 1, 0, 1, 1. Compared to this, quantum mechanically, a 2-qubit quantum register may contain these 4 states at the same time. Within the blue box, there is the quantum description of a 2-qubit register, which tells that the 0, 0, 0, 1, 1, 0, and 1, 1, all these 4 numbers are stored within the 2-qubit system. But what if we did it 2 of these 4 numbers, and we use only the cat 0, 0 and the cat 1, 1, so the classical 0, 0 and the classical 1, 1 value. This can be modeled by a stick which connects or glues the 2 coins, and the coins are rotating together in a synchronized ways. In that case, we have 2 possible outcomes, either 0, 0 or 1, 1. Okay, if we do this experiment by 2 quantum bits, for example 2 electrons, then the result will be different. I explain you this experiment in the following way. We ask Alice, I don't know whether there is Alice in the room or not, but we ask Alice, thank you. So we have a realize. So we ask her to take one of the quantum bits, one of the 2 electrons, and travel to Sydney to the Opera House, and we ask Bob to take the other quantum bits and travel to New York to the Metropolitan. And exactly at noon, we ask Alice to measure, to check what is the value of his quantum bit, and she can either measure or look 0 or 1, because both values are stored in this composite system. But if Alice measured 0, because the system, the joint system, has only 2 possible joint states, 0, 0 or 1, 1, so if Alice measured 0, then we can be sure that Bob will measure 0, 2. If Alice measured 1, then we can be sure that Bob will measure 1, 2. And this will happen even in the case when the time difference between the two measurements is so small that even the light cannot travel between the two locations. So it seems to be that there is an effect which is faster than light. We learned from the relativity theory that the speed of light is an upper limit, but speaking correctly, it is valid for the information delivery, and in this case there is no information which is travels between the two points, but this special phenomenon called entanglement, because the two particles, although they are moved in distant places, are in a very strong connection. If we get 0 on one place, the other place, on the other place, there will be 0, 2, and similarly with the ones. How can such strange states generated? This is an entanglement generator from the Quantum Information National Laboratory used for free space quantum communications. So on the bottom left, you can see a laser device. The laser beam goes to a special crystal, a lithium niobate crystal, and there are two beams of photons coming out from these crystals, and these photons are entangled. These photons are in special state regarding the polarization. Considering entanglement, it is very interesting and important that if the entanglement is unwanted, so is generated by the nature, then this is the main bottleneck of quantum computers. Because you can imagine that I have a quantum computer, and within this computer there is an electron whose spin is entangled with another electron in a butterfly flying outside of the Academy of Sciences. And if we measure the butterfly, then it will influence the operation of my computer. So this is a real problem and a real challenge. On the other side, all the actually known quantum algorithms, which are more efficient than the classical counterparts, they are using entanglement, but intentionally generated entanglement. So entanglement is a very important resource in quantum computing and communications. So the third postulate describes how the time evolution of quantum systems work. Practically, we can model them similar to the classical digital technologies where we use elementary XOR, inverter, or other gates. A similar description exists for the quantum world, where we can use, of course, special quantum gates to describe any operation on the quantum bits. And because these quantum bits can be described according to von Neumann by unit-length vector, therefore, we can visualize the operation of a quantum computer by means of a rotation on the surface of a sphere which has unit radius. Okay, sorry. The last and fourth postulate is the so-called measurement or quantum to classic converter. Unfortunately, during the last several million years of evolution, the human race did not develop any senses for the nanoworld. So no one had the opportunity to see an electron or a photon. We try to measure them. We have some information about these elementary particles, but we are not really familiar with its original nature. Therefore, the measurement is very important because it helps us to get information from the quantum level of the systems. Practically, this can be modeled when this coin is flipping in the air. I hit the coin, it will fall down, and either it shows the tail or head. So this is practically a measurement. And there is a famous thought experiment, probably you heard about that. This is the so-called Schrödinger cat paradox, which is nothing else than if we have a quantum world all around, so especially myself, I am consist of plenty of quantum bits. So I can be described by means of a very huge quantum register, of course. But our experience is that if we go or step out from this level of quantum region towards the classical world, towards the size of a human, this quantum behavior, these quantum properties somehow disappears, and this Schrödinger cat's paradoxon somehow tries to explain this strangeness. And even John von Neumann was really interested, because this is somehow related to the philosophy, when and how change we from quantum to classical. So therefore, he has results on quantum measurement, how to describe or how to design measurement in quantum system. And this type of measurement is called or named after von Neumann as von Neumann measurement, and we teach this measurement technique for students at the university. Okay, so altogether I listed here the postulates of quantum mechanics in engineering context and listed the formulas, so there are mathematical formulation behind these postulates. Now I would like to give you a short history, not quantum mechanics, but for the quantum computing and communications. Okay, the starting point in my presentation is the 5th Solvay conference. This was a conference where scientists were collected, especially physicists who were dealing with the quantum mechanics and try to finalize and formalize the rules of the nature in the quantum regime. And you know, parallelly, there was another big effort to describe the large dimension of the universe. How many Nobel laureates did we use to invent or discover the rules of the large distances? Okay. One or half, because Einstein was the person who, but he received the Nobel prize not for the relativity theory, but the photoelectric effects. On this picture, on the top left, so these are the conference participants. There are 15 Nobel laureates who were or related somehow to this quantum mechanics. So you can imagine that the intellectual effort which was needed to finalize and describe the nature at this low level. Thanks to John von Neumann, his book was mentioned before, there was a strict mathematical formulation of quantum mechanics, and Richard Feynman, who was also a Nobel laureate physicist, was the one who published the paper, and he mentioned that maybe it is the time that not only physicists work with the elementary particles, but maybe engineers can think of how to use them for computing. And this was the start of the quest for the quantum computers. There were many ideas how to build or what type of physical objects could be good quantum bits, but it took plenty of time to find appropriate solutions. But in the meantime, mathematicians, engineers were thinking of how to apply, how to use later if we will have real quantum computers. And many algorithms and protocols were born during this period. And even we realized that there is an algorithm called the Shor algorithm, which is able to crack the widely used RSA and public key type of security systems. Therefore, a new track had been initiated, which is the quantum communications. So how can we communicate in a secure way so that even a quantum computer cannot break this code? So one track is this quantum communication. Actually, there are two segments. One is optical fiber-based ground segments or terrestrial segments of quantum communication, and the other is the satellite-based free space segment. And around 2018, some computers were published or were accessible, which we believed that they are more or less really operating in the quantum regime. However, there are true texts even nowadays. One is the quest for the universal quantum computers, which can be programmed to any problem and can solve it very efficiently. And the other track is to develop quantum computers for specific problems. And it is a good question from engineering point of view. What type of programming languages are good enough so that the human logic, which is which were strengthened on in the classical world, so how can this logic translate it to the quantum world, which has a bit different system of rules? And similar to the classical info communication, where you realize that a mobile phone is a computer stronger than the computer which was used to land on the moon. So this is a very serious computer. On the other hand, this is a communication device. So computing and communications integrating during the last several decades. And we expect that in a similar way, quantum computers will be connected so that to generate a higher impact than single standalone computers. The European Union realized that a centralized effort is needed in Europe to be compatible or compatible with the US or the Asian countries. Therefore, in 2016, a manifesto, a so-called manifesto, were published, which described 6 areas of quantum technology, and among these areas there is the quantum computers, the intercity quantum link, the satellite link, and the optical fiber-based quantum internet. Practically there are 4 directions, merging directions: communication, computation, simulation of quantum systems, and sensing as well. And taking into account that my time is limited, I brought you only one quantum algorithm to show the efficiency of the quantum computers, and this is related to this not machine learning, to searching and database handling. Okay. You are familiar with the fact that we are collecting information every second. Terabytes of information are collected from the shops, from the communication network, and whatsoever. But this information is useful if we can process this information. And one important problem is the searching, to find a certain element in a very huge database. This problem is as old as the human race, because practically the Stone Age people, when they would like to find something to eat, they had to go to the nature, and the nature is practically an unsorted database. They spend plenty of time to find berries and animals. Is anyone who knows what is the solution of this problem? How did the Stone Age people improve the efficiency? Sorry? Yes, but I have a more general answer. This is agriculture and animal husbandry, because if you need a sheep, go to the shepherd. If you need an apple, go to the apple garden. And if you need a car, go to the garage, and so on. So practically, from computer science point of view, agriculture and animal husbandry means sorting the database. And for the past 10 millennia, we did the same. We always sort. Maybe you have the experience when you visit a large shopping mall or a hypermarket. After several visits, you find the bread, the milk, and what you would like to get. But next time to go to the shop, suddenly this sorted in your mind database becomes unsorted because the guys who run this shopping mall moved to different locations the goods. Therefore, you need to spend more time. They decrease your efficiency to find the goods in the shopping mall. So they make the database unsorted. Fortunately, there is a quantum algorithm which is able to find a certain element in an unsorted database. So there is no need for sorting. This is called the Grover algorithm. Here you can see on the left-hand side this block diagram of this algorithm, or this we call it Grover operator. On the right-hand side, it shows that this is practically nothing else than rotating the index vector of the database to the appropriate position, and the efficiency of this algorithm scales with the square root of the size of the database. However, from engineering point of view, the finding an element is important, but not so important. What is important to finding the smallest or the largest element in a database? Because typically we engineers optimize so-called goal functions, and we would like to find the optimum solution for a problem. Therefore, this is a result from this Quantum Information National Lab. We had a modified algorithm called quantum existence testing, which is able to decide very efficiently whether a certain element is contained by the database or not. And if we combine this quantum algorithm, this quantum existence testing, with classical logarithmic search, which itself is very efficient for sorted databases, then in that case, here there's an animation how it works. So we can find very quickly the smallest value in the database. So this is I'm saying as a beautiful result because we had a very quick classical algorithm, but it is not able to be used on unsorted databases, but involving a quantum solution and combining them, we can provide a quantum assisted solution to this problem. Okay. Here, with my PhD student, made some calculations or tested the efficiency of this algorithm. Probably you know that actually nowadays big server farms are used to collect the data and run different processes. So they collect the information, the data from all over the world, make the processing and send back the information or the results. And on this figure, you can see the blue one represents a classical solution, and the red one is the quantum assisted solution to this problem. If you are interested how to imagine a quantum bit, there are several promising solutions. One could be the usage of the spin of an electron. This is a magnetic property. So an electromagnetic field, by means of an electromagnetic field, we can set up the quantum bit in a superposition state, so it can contain an upwards and downwards state of the spin at the same time. The problem of this approach is that it is very sensitive for the environmental noise, and practically we would like to build several thousand qubit long or large quantum processors. Therefore, it seems that this type of approach is good for proving the concept, but not good for the everyday use. Another possibility, the so-called Cooper pairs, the superconducting electron pairs. They are very good or appropriate solution to store quantum information. The only requirement is that the device has to be cooled down near to 0 Kelvin. So the device itself is like a melon, and everything which provides this, the frigator is like a room. Okay, another possible solution is the ion trap, where ions are stored or carried again in electromagnetic field, and the energy level of these ions carries the quantum information. And the last but not least solution is the photonic quantum computers. These are very promising and as a new approach, because photons are very resistive against entanglement, so they are very solid and good quantum bits. The only problem that photons travel with the speed of light, so it is hard to keep them in a certain location. And here there is a figure about the different potential technologies of quantum computers, and I put this yellow dashed line. This is the Moore's law in the quantum regime. It is called Rowe's law because after another scientist. But you can observe that there are certain technologies which may probably continue the Moore's law for quantum computers as well. Of course, there are so-called sure bet technologies. Probably they will be the winner of this competition, but we are not sure. There are several ones which are risky or less reliable. I take among them one, which is this is the IBM's quantum computer. I prefer it from educational point of view because they made publicly available of the small qubit quantum processor. So even undergraduate students from the university can write codes and programs on the processor, send to the cloud, and they run this code on this processor. So you can follow here the different dates and the different numbers of qubits. This is an exponential increase in the number of qubits. Of course, these are the so-called classical qubits, and the really useful operational qubits, which can be used for computation, its number is smaller. So, but we think that Moore's law is still alive in the quantum regime. And here, I would like to only highlight how many companies, different companies, are working on quantum computing, different aspects, of course, computers, programming, applications, and so on. From computer science point of view, if you would like to write a quantum algorithm, which is more efficient than the classical counterparts, more or less it seems to be easy, because every quantum algorithm contains an initialization which can be written in several rows in a program, so it is a very clear and easy job. To define the parallel computation of the quantum computers, it is more or less easy. So after some practicing, you can do this. You can construct measurement thanks to von Neumann, and sometimes we need post-processing to evaluate or understand the results. But the really challenge is the so-called amplitude amplification, which makes the originally inherent randomness in the quantum regime more or less deterministic. So it influences or modifies the probabilities in the quantum regime, so that if we make a measurement, the appropriate answer will be get. And here is an example from Microsoft. This is Q# for a quantum code, and this is the IBM's Qiskit, which is a Python-based quantum programming language. And some results and interesting about quantum communications. The most famous communication protocol is teleportation, not because we would like to teleport anyone in this room or later in the future, but from information theory point of view, the teleportation is nothing else than an entanglement assisted. This means that we use entangled quantum bits for assist the communication. So this is an entanglement assisted transmission of quantum states over classical channels. So it makes it possible that we use classical commercial optical fibers to deliver quantum information. So it is the real importance of the teleportation. And as I mentioned earlier, so the aim of quantum communication is to connect quantum computers and sensors in a large network. And the so-called killer application, the first application which is actually under spreading all around the world, is the so-called quantum key distribution. This is the Gartner hype curve. Quantum key distribution means that we encode classical information into non-orthogonal quantum bits, and thanks to this encoding, if anyone tries to get information from the channel, we can reveal this eavesdropping event. The other, excuse me. The other item on this curve is the post-quantum cryptography. This means classical efforts to find such classical ciphering algorithms which are resistive against the quantum computers. But because we don't know what are the limitations of a quantum computer, we cannot say that an algorithm really resistive against the quantum attack. Okay, here is an optical fiber which is used for terrestrial quantum communications. For the sake of comparison, this diagonal black strip is a hair, a strand of hair, and the red one is the core. This is the real part of that, so the optical part of the cable which is used, and we send photons into this small optical or narrow optical cables, not as a bunch of photons as in classical communications, but one by one, and modify the polarization of the photons one by one, and this carries the information. The other segment, as I mentioned, the satellite segment, this is a Chinese satellite. It was launched 2 years ago and made a connection between Graz in Austria and a city in China, and demonstrated that quantum information can be delivered by these 2 distant points. ESA, the European Space Agency, plans to launch the European quantum-capable satellites within 3 or 4 years, and we plan to deploy a receiver station here in Hungary. This is the Hungarian results. Last year, we deployed a testbed in Budapest. It had on the right-hand side a free space optical link between the building of the Budapest University of Technology and the opposite side of the Danube. There is a building of Vodafone. So it was roughly a 1 kilometer long free space optical communication test, and the other was towards the Wigner Institute of Physics in Csillebérc. This is roughly 10 kilometers, but we use the commercial cable, optical cable of the Hungarian Telecom. So, and this is 2 devices of the fiber-based quantum communication system. These were developed at the Department of at the Faculty of Electrical Engineering and Informatics, together with the colleagues from Wigner and the Faculty of Natural Sciences at the Budapest University of Technology. And what we are doing now, we are working on the Hungarian backbone of a quantum network. We are good progress towards Pozsony, Bratislava, and Vienna, Bécs, and there are several other directions toward Pécs, Szeged, and maybe Miskolc, so that big Hungarian cities will be connected by means of quantum devices. This is supported partly by the European Union, partly by the Hungarian government, and next year there will be a call for the cross-connection of the national networks in order to implement a pan-European quantum communication network. So, as a summary, I presented you that we started as engineers roughly after 1930, when the postulates and description of quantum mechanics had been formulated. John von Neumann had important role in this formalization, especially according to the mathematic description of the quantum postulates and operation. But the real work with the elementary particles from engineering point of view started around 1990. In 2010 is the year of the first successful communication experience. 15 is the commercial quantum communication devices, and around 22 there are quantum computers. I wrote here mainframe, similar to the classical big computers, which has distant access and can run difficult problems. And the novelties are the small-case quantum networks, which will be later interconnected. And I started with the walnut tree of John von Neumann, and I would like to finish my talk also with him. Every last lecture of my courses on quantum technology is held in the nature. There is a statue of von Neumann roughly 200 meters away from our building. We go there with the students, and I tell them the story of quantum mechanics and quantum technology, and I highlight the Hungarian participants of this process, among them, of course, John von Neumann. So thank you very much for your audience.